Hello to everyone. I am Reinaldo Santos de Lima, and be welcome to the seminar of the Astronomy Department of IAG-USP. Thank you all for your participation. And today we have the pleasure of having the presence of Dr. Nicolas Martin from the Observatoire Astronomique de Strasbourg. Dr. Nicolas, thank you for accepting this invitation. Some short bio about Nicolas. He got his PhD from the observatory, the Strasbourg. Then he moved to Germany, where he worked as a researcher at the Max-Planck Institute for Astronomy. And then he moved back around 10 years ago to the Observatory of Strasbourg, where he has a tenure researcher position. He is an expert of galactic archaeology, and he's co-leader of the Pristine Survey, which he's going to talk a little today for us in his seminar, which is named the Pristine Survey, Galactic Archaeology with the very metal poor and very old Milky Way. Questions can be asked to Nicolas after his presentation. If you are following the seminar in our YouTube channel, you can write down your question in the chat. And I would like to ask everyone to please turn off microphones and cameras during Nicolas' presentation. And Nicolas, please feel free to start.
Thank you very much. I apologize for all the French names there. It is sometimes a bit difficult to pronounce. Thank you very much for the invitation. The pandemic hasn't had many good sides, but one of the good sides is that we can have now quite commonly these online seminars and present our work to institutes on the other side of the planet. So I very much enjoy the invitation and the opportunity for me to present the work that we've been doing with the Pristine Survey, which is a photometric survey of the northern sky of the Milky Way. You see the footprint here on that first slide, overlaid on top of the Gaia image of the sky, showing the Milky Way with the disk of the Milky Way, the beautiful disk of the Milky Way, the imaginary clouds down there that you're lucky enough to see in the sky in the southern hemisphere, and the red footprint is the coverage that we've made of the Milky Way sky with this particular photometric survey that allows us to get the metallicity of stars, and in particular to focus on the very low metallicity stars. So I'll explain why this is interesting, what we can learn from it, and I will show you how the survey works, and then go quickly through a series of different types of science that we can do with the survey. But before I launch into it, I must also mention my colleagues in the collaboration, the Pristine Survey in particular, Elsa Stackenberg, who's co-leading the survey with me, and this great group of about 40 people. I've highlighted here the colleagues who are in Strasbourg and working more closely with me. And the work that I'll present today would not have been possible without this large group of people, and also without the Canada France Hawaii Telescope, the CFHT, which has been really the pillar of the survey and has allowed us to get all that photometry, all these images, this photometry that I'll be talking about today. So I first want to have a very broad introduction on galactic archaeology. What do we mean by galactic archaeology? It's one of these buzzwords that we hear about a lot, that's thrown around a lot, especially now in the era of Gaia. To me, galactic archaeology has two sides. In both cases, it's understanding how the Milky Way was brought together, was assembled over time. But I separate two different parts. One of them is, for instance, searching for the leftovers of the Milky Way assembly in its halo. For instance, the dwarf galaxies, the globular clusters that came in a little too close to the Milky Way, were attracted by the Milky Way by gravity and then thrashed, transformed into stellar streams around the Milky Way. And when I say the Milky Way, this phenomenon is present around every single galaxy. It's just that we can only observe it within nearby galaxies where we can get observations that are detailed enough. And by looking at these stellar streams, they're the fossils of the accreted systems onto the Milky Way, and that's evidence of this hierarchical formation of galaxies that we all know exists and has existed for the last 13.7 billion years. And you see an example of this hierarchical formation of galaxies in the halo of the Andromeda galaxy. It's this image on the right here that we did almost 10 years ago now, from observation of the PANDAS survey, which was a photometric survey tiling the surroundings of the Andromeda galaxy, this beautiful disk galaxy, our cosmic neighbor, that we usually see just as this disk galaxy. We think it's not too different from the Milky Way, maybe a bit more massive with a bigger bulge, but compared to other elliptical galaxies or smaller, bigger galaxies, we think it's quite similar to the Milky Way. And so what we did is that we mapped the surroundings of Andromeda, and by looking at the density of red giant branch stars, we were able to map all of the structures in the halo of Andromeda out to distances of 150 kiloparsecs. And the color here of these various structures represents the metallicity of a structure. And so here we do see galaxy formation in action, hierarchical formation of the galaxy in action, where we have all of these stellar streams that are coming from dwarf galaxies, like these blue dots, that have been tidally stripped and left in the halo of Andromeda their stars. So by going in the halos of the Milky Way, or the halo of Andromeda, and looking at the detailed properties of these fossils, we can hope to understand how the Milky Way pulled itself together, for instance. And then to me, there's a second side to galactic archaeology, which is looking at the oldest stars to, again, try to understand how the Milky Way pulled itself together, but it's very, very infancy. So if we were able to find the oldest stars in the Milky Way, then we'd be able to say, oh, okay, they're on these orbits, they came in this way, and that's how the proto-Milky Way was assembled in the first 1, 2, 3 years of the age of the universe. But unfortunately, age is a very difficult quantity to measure in stars. We can do it through astroseismology with very high precision and accuracy sequences of photometry, but that only works for very, very bright stars. If you take a random star in the halo of the Milky Way, it's very hard to know its age. But what we can measure quite easily is its iron abundance, its metallicity, which here you have on this scale, this Fe/H, is the iron to hydrogen ratio present in the star compared to the sun. So if you're at 0, your solar metallicity, the sun is by definition at Fe/H at 0. If you're at -2, you have a 1% of the solar iron to hydrogen ratio, and at -3, you're 1 in 1,000, and so on and so forth. And what you can see from, for instance, from these simulations it's a plot that I took from Karim Baldry's paper in 2018, is that as the Milky Way, or as the universe forms stars, what happens is that the first stars die, and they spew out the heavy elements that they form in the fusion reactions at their core. And then the next generation of stars that will be formed from the interstellar medium that's been polluted
I think we had some technical problem. I would ask everyone to wait some minutes, some seconds. Okay, probably Nicolas lost his connection, so let's wait a couple of minutes, or even less.
I'm sorry.
No problem. Probably okay. You lost connection. No problem.
My network never drops, and it just did. So
it happens.
I apologize for this.
No problem. Whenever you want, you can resume.
Right. Okay. Let's hope this doesn't happen again.
It's fine.
All right. So I'm not quite sure when I dropped off, but effectively, as you measure the metallicity of stars, if you're able to measure, to find a clear sample of stars with very low metallicity, you're able to probe the behavior of stars in the very first gigayear or two of the age of the formation of a galaxy like the Milky Way. So with these two different pillars of galactic archaeology, let me just focus now on the reason to do a low metallicity survey of the Milky Way. One of the first goals to do so is to find these most metal poor stars, those that might be linked to the very first generation of stars. We think that these very first stars were quite different from the current stars. At the start, at the beginning, soon after the Big Bang, the stars were made entirely of hydrogen and helium, and a little bit of lithium. Because of this, they had to be very, very massive to be able to form. And because they were very massive, they most likely died very quickly. And we're probably unable to reach these very first stars. But if we're able to find stars of second, third generations, maybe we can see what elements were producing these very first stars. So by finding the lowest metallicity stars, we can get closer and closer to how the first supernova exploded, what the first stars were, and what their properties were, which is essential because, of course, this is at the foundation of every stellar formation that happens later in the universe. And the other reason to do a metallicity survey of the Milky Way that's tied to galactic archaeology is that it allows us to do this metallicity decomposition, for instance, of the halo of the Milky Way, get rid at some level of the stars in the foreground that are part of the Milky Way, were formed in the Milky Way, to try to focus on these fossils of past accretions by looking in the halo, especially nowadays with the Gaia astrometry that tells us a lot about the movements of stars. It's easier to select halo stars, but Gaia, at least until next June, and it does not provide an accurate metallicity for most stars, and even next June with the next release of Gaia, there will still be many, many stars for which there isn't an accurate metallicity. And so if you want to do a survey of metallicity of stars in the halo of the Milky Way, you have really two broad ways of doing it. The first one, which is probably the best way of doing it, is to do large spectroscopic surveys, observe millions of stars, tens of millions of stars, and get spectra for these stars. So you can derive the metallicity, but also other information, for instance, the chemistry of the stars, its chemical abundances, its radial velocities, and so on. Unfortunately, this is incredibly expensive. It's only now that we're starting to have really broad surveys like SDSS that started 20 years ago, but nowadays DESI, we foremost, that are really pushing for multi-million spectroscopic surveys, and we're only talking multi-million, usually less than 10 million stars observed over a period of 5 to 10 years. Another way to get the metallicity of the stars is to, and that's what we did with the Pristine Survey, is to do narrowband photometry. With a particular filter that focuses on the part of the spectrum of a star that is metallicity sensitive. By doing it this way, it's significantly cheaper. You get the metallicity of tens of millions of stars. Of course, you don't get as much information as you would with a spectrograph, but then you can think of teaming up with a spectroscopic survey, as we did with Pristine, so that you have an efficient way of isolating stars of interest based on their metallicity, the photometric metallicity, and then follow them up with spectroscopy. So you invest most of your spectroscopic survey time in stars that are actually really interesting. So I want to show you first how the Pristine Survey works and how we get the metallicity out of this narrowband photometry. It's nothing new. There's similar surveys that have been done and pioneered in the 80s, although people used to at the time, they tended to use Prism Photometry, so replacing every single star, the image of basically instead of having an image where you see the stars, you put a prism between the photons and your focal plane, and you end up with every single star becoming a small spectrum focusing on the region of interest, and then you try to get the metallicity of your star out of this very small spectrum that you get. Unfortunately, when the crowding is strong, when your stars are very dense on the sky, then these little bit of spectra overlap. And so that's not an ideal way to do it, because now we have access to filters that are very efficient and very narrow and very well behaved, in the sense that they're very top hat, irrespective of where you look on the field of view. The filter that we're using for the Pristine Survey, which is shown here on the right, this calcium H&K filter, centered between the typical U band from the SDSS and G band from the SDSS. It's very narrow. I'll show you a zoom in that region. It focuses on 2 lines that are present here. If the filter was built in 2014, if you go back 5-10 years, it would have been impossible to build a filter like that for this camera. So it's very much something that is possible right now, and wasn't possible when the Prism Photometry surveys were done in the 80s and the 90s. One of the benefits we have is with Pristine is that we can rely on the megacam imager on the Canada-France-Hawaii telescope, which is an imager with a 1 square degree field of view, so it's 4 times the size of the moon, so we can quite efficiently tile the sky. And we keep it a bright survey. We only try to reach down to the depth of the Gaia data, so that allows us to do short exposures and to tile as much of the sky as possible. And to improve even more the amount of observations that we can get, we've actually put together a bad weather program so we can observe when effectively no one else wants the telescope. And that's how we've been able to accumulate more than 130 nights of telescope time since 2015, tiling about 6,000 square degrees in the Milky Way sky, which is the footprint that I was showing you earlier in the talk. It's not quite up to date. I realized when I was putting the seminar together, we have a bit more coverage right now, but effectively you can see here that it's a survey that's focusing on the North Galactic Cap here and the South Galactic Cap over there. We're staying very much in the northern sky. The reason for this is that in the south, there's a similar survey called Sky Mapper that focuses on the southern sky, and we see no reason to go and fight each other for the south or for the north. So we kind of each have our own hemisphere. And also because a lot of the follow-up that we'll do in the coming years will be tied to the WEAVE spectroscopic survey. That is a northern sky survey. So we're trying to tile as much of the northern halo region as we can at the moment. And we have an extension towards the Bulge, the central Milky Way, the PIGS Inner Galaxy Survey, or PIGS, the Pristine Inner Galaxy Survey, or PIGS, which is PI'd by Anke Aronson, postdoc in Strasbourg, and I know that she's going to tell you a lot about this in a couple of months. I think she's giving a seminar on the same platform in June, if I'm not mistaken. So the images, we usually show these beautiful images in astronomy. Let me for once show you a really boring image. This is what our typical image looks like. These are short exposures observed in the very blue, so you have very little sky. So you see the electronics, the readout noise, and you see a few stars here and there. And that's basically what our observations look like. So how do we get from this type of photometry to getting the metallicity of a star? Well, let me go through a set of artificial spectra of theoretical spectra and show you how they behave and what kind of magnitudes we observe with that filter for these different spectra of different metallicities. So this is, for instance, the spectrum of a typical low red giant branch star of solar metallicity. And what you can see is that we have here the calcium H and calcium K line that are very, very broad in this particular at this particular metallicity, because there's a lot of heavy elements in the spectrum, a lot of calcium in this case, but that correlates with iron, that absorbs a lot of the photons from that would otherwise reach us. The dashed line here is the top hat filter, calcium H&K filter that we're using. And so what we can do is test different theoretical spectra, for instance, for different metallicities, for different temperatures. And so you can see that as the temperature changes, the depth of these lines, they still remain very broad, but they do change. So we need a proxy for the temperature to figure out how much absorption we should have, to figure out how much, what the metallicity of the star is. So to do that, we can, for instance, use broadband GNI from SDSS. And then what we can do is plot on this color plot on the left, on the x-axis GNI, which is a proxy for the temperature of the star. So this is where the three spectra that I showed will lie in this color range. And then on the y-axis, what we can show is the magnitude in that calcium H&K filter compared to the magnitude in the G-band just to the right of it. Effectively, the G-band tells us how much continuum we expect. And then by measuring the calcium H&K magnitude under this filter, we know how much absorption and therefore how broad these lines are here. And so for these three spectra on the left, this is where they lie in that color space. And that term here is just a way to rotate that space so that the middle rich stars are at the bottom and the middle poor stars should be at the top. Now, if I take a star with a low metallicity, an FE/H of -1, so a tenth of the solar metallicity, you can see from the spectra that the lines get narrower. That's expected because you have fewer heavy elements, you have less absorption, so your lines are not as deep. And so then we can look where these stars would lie in this color plot. And that's somewhat disappointing because there isn't much of a discrimination between the stars of metallicity 0 and -1. But let's look at what happens when we reach the lower metallicity that are the most interesting to us. If we go to metallicity -2, 100th of the solar metallicity, we see these lines that are getting significantly more narrow. And then these three spectra, if you integrate it under the filter as I described before, then they would lie here. And then that becomes interesting because it would be very easy to discriminate between a star in metallicity -2, which would be over there, and a star in metallicity -1, which would be down there. We're talking about a difference of 0.2, 0.3, 0.4 magnitudes, which is very easy to measure with CCD photometry. And then if we continue that exercise, go to metallicity -3, the lines are even more narrow, and the stars should lie even further up in that plot. And then we can continue like that until we reach infinitely low metallicity, so basically a star that contains just hydrogen and helium, and then you end up having this upper limit of where the stars should lie. But that means that if this is all accurate, if we have the position of a star in this diagram here on the left, we should be able to derive its FE/H, its iron metallicity, quite easily without too much trouble. That's the theory. Does it work in practice? The answer is yes. As soon as we have a few hundred square degrees of pristine photometry, what we were able to do is go in the Segway spectroscopic archive and extract all the stars that overlap with our photometry. And the good thing here is that we can use Segway and the spectroscopic metalicities in Segway to tell us where real stars lie, color coding them here on the two panels by their spectroscopic metallicity. And if everything works well, you should have all the metal-rich stars, the red stars at the bottom, and all the metal-poor stars, the blue stars at the top. And this is indeed what happens, especially after you've cleaned out a few weird objects like variable stars or quasars or white dwarfs and so on and so forth. So you end up with a very clean diagram that tells you that you can use this color plot as a diagnostic of what the metallicity of a star is. And even more interestingly, these lines here, these that you sometimes have issues seeing on top of the dots that represent individual stars, corresponds to the models that I was showing you before. So there's a very good agreement with the models and the observations from the Segway spectroscopic metallicities. So we then developed a model that allows us, from knowing the position of a star in this color plot, to effectively derive a photometric metallicity for the 10, 20 million stars that we have observed in the Pristine Survey. And so we can compare that with previous methods that were used. For instance, a common method as soon as SDSS started producing photometry was to use the broadband from SDSS. The U band, the very blue band in SDSS, is actually quite metallicity sensitive. But you can see by comparing the photometric metallicity obtained from particularly the blue U band and the spectroscopic metallicities from SDSS, which are the truth in this case, you can see that that technique is not very efficient at telling you that a star is very, very low metallicity. There's some kind of saturation that happens. The broadband photometry is not able to discriminate between a star metallicity -1.5 and -3 or -4. But in our case, we're much more sensitive to this. And so we're able to get a pretty good understanding of whether a star is metallicity -1, -2, -3, just from the photometry that we get combined with broadband photometry from other surveys. We've been using SDSS, but we can use, and we have been using also now Gaia, which is very well calibrated, or other broadband from PanStars or many other surveys that we piggyback on to get the results that we want. So with these basic functioning of the survey out of the way, let me focus on some science results that we've been getting now that we have the photometric metallicities of stars in the Milky Way halo over about 6,000 square degrees. And I'm going to focus on 4 science results, and I'll go fairly quickly on every single one of them to give you a teaser, and I'll be very happy to go into a bit more detail during the question time afterwards if you're interested. So first thing we did is launch into a very broad spectroscopic campaign to, first of all, make sure that we knew what we were doing, that when a metallicity from Pristine said that the star looked like it was very low metallicity, that it really was very low metallicity. And there, the only way to really confirm that is to get a spectrum and get the metallicity of that star. We did this very large spectroscopic campaign, adding more than 150 nights of telescope time, mostly small telescopes. But still, it was pretty grueling work observing stars one by one, because you can't rely on multi-object spectroscopy because the density is too low on the sky, and you do have to observe the stars one by one. So we sent many people to the telescope, and I spent many nights at the telescope. But it was actually quite rewarding because it allows us to show that Pristine, in fact, does work as intended. And it allows us, amongst other things, to do to study the low end of the Milky Way metallicity distribution function from the more or less 1,000 stars we've accumulated over the last few years. And so this is the first, I'll show you these results in just a second. This is the first step of that spectroscopic campaign. Now we've reached a stage where getting another 10 nights or another even 50 nights would not significantly increase our sample. And so we've stopped doing that kind of follow-up, and we're waiting for the Weave spectroscopic survey to start it was supposed to be in 2019, 2020, but because of technical difficulties and then the pandemic, it will only have its first light in a few months. And so we're eagerly awaiting, because we have an agreement with Weave that they will follow up the candidate extremely low metallicity stars that we will give them. And we should get about 30,000 stars observed down to magnitude 20 in the coming 5 to 7 years. But what we've been able to show with the first step of that spectroscopic campaign is that indeed, when, and this is a bit of a busy plot, I apologize, let me just drive you through it. What you see on the left here is, on the y-axis, this is the metallicity that Pristine gives to a star. And on the x-axis here, this is the metallicity that we got out of the spectra that we observed from the spectroscopic campaign. And the first thing you can see is that if Pristine says a star is below metallicity -2 or below metallicity -2.5, actually 70 to 80% of those stars really are below metallicity -2. So even if we get things somewhat wrong, we don't get it very wrong. We're still looking at the very low metallicity Milky Way, so the halo stars that were probably brought in quite some time ago into the Milky Way. The other thing you see if you focus on this region here at the low end is that stars should lie on this one-to-one relation. They don't. So our model is not perfect, far from it. But we know where this is coming from, and this is coming from the fact that SIGWAY that we calibrated it onto is not that good, even with spectra, at getting accurate metallicities below -2.5 or -3. And so now that we have this large sample that will be increasing with time, we're going to iterate and just rebuild our metallicity model so that we improve it and get as close as possible to the one-to-one line. But the bottom line is that where the previous generation of surveys used to have an efficiency of 4% to find a star of metallicity -3, we're at about 20–25%. It's significantly better because the filter is better, the technique is more refined, and so on. It's just the normal evolution from these pioneering surveys to where we stand now. And as I said, the other really good benefit is that when we observe a star, usually it is very metal poor, and we don't have many high metallicity stars that end up in our sample. And so with this sample of about 1,000 stars, of course, one of the things we were looking for were incredibly low metallicity stars, those that have a metallicity F/H less than -4. There's about 45 known to date. And these are the closest to this first generation of stars. And we did find a couple. One of them very early on was this one. I always find it fascinating when you look at a spectrum of a star like this, you see basically hydrogen, and then this tiny calcium line, and then just hydrogen and nothing else. And what was quite interesting with the star is that actually it contains very little carbon. These small wiggles are probably due to some carbon in that star. But the typical star of that low metallicity tends to be very carbon enhanced, and it's not subtle. It tends to be something like this. And so this star, if you count all of the heavy elements that are present, carbon plus iron, etc., it might actually be the second most metal poor star ever discovered, because it does not contain a lot of carbon, whereas most lowest metallicity stars contain a lot of carbon. So hopefully in the coming years, especially with the Weave follow-up, we'll be able to build a sizable sample of a few dozen of those stars to try to build statistics on what that tells us about how the first supernovae exploded and polluted these second, third generation stars. So now I want to move to the second set of science results, which is work that was mainly led by Federico Sestito, a former PhD student working with me, who graduated a bit more than a year ago, and he's focused on the orbit, the kinematics of these extremely low metallicity stars that probably date back to the first couple of gigayears from the formation of the Milky Way. So if I go back to this idea of hierarchical formation and maybe the naive idea that we have of how a galaxy like our own should form with time, is that if you go to very high redshift, you basically have a set of clumps of dark matter that have started forming a few stars, but mainly contain gas and dark matter. And we think that through gravity, these assemble to form a proto-Milky Way. These initial stars that were blue in the very first panel get older and become redder with this color coding, and they distribute themselves in some kind of spheroidal distribution because they're probably coming from multiple small blobs that merge together with random orbits coming from all places. And then from there, you start, the gas settles, your Milky Way starts forming, but the oldest stars that were brought in from these initial contributors, naively, we would expect them to be distributed in a spheroidal fashion, a pressure-supported spheroidal system that you can call the inner halo, you can call it the bulge, but it should be pressure-supported. And so what we did with Federico is actually look at the orbit of these stars, the stars with the lowest metallicity node, to try to figure out whether that scenario was what we were seeing with the stars around us. And we're able to do that thanks to Gaia, because before we had Gaia and the constraints on the parallaxes of the stars, usually for a typical star in the halo, you have two solutions, or a typical star that you observe, you have two solutions. Either it's a dwarf, it's very close by. This is the PDF, the probability distribution function that you would get if you assume you have no distance information whatsoever. You get a very strong peak at very low distances. That's the dwarf solution. And then you have a very broad peak that you can barely see here that tells you, oh, maybe it's a giant that's far away. And usually that's the two solutions you have and you're a little stuck. But thanks to Gaia, even when the parallax is not very accurate, like in this case here for this one star, Gaia is good enough to tell you maybe the parallax is not accurate, but Gaia knows that it's not compatible with the distance of a very, very close by star that would have a parallax information that peaks around here. So when you combine all that information, you end up with a posterior distribution, probability distribution on the distance to that star. And since now you have the distance, you have the proper motions from Gaia, and you have radial velocities from other surveys or other sources, you can get the orbit of the star. And so in doing this careful work, Federico was able to build the orbit of the most middle polar stars that we had access to. And most of the stars look like this, and that's kind of what you expect. What you see here is the XY plane of the Milky Way, XZ and YZ plane of the Milky Way. The sun is shown by this green symbol here, and the blue wiggles represent the orbit that is followed by the stars that orbits in the inner halo in this case. And then the gray line corresponds to drawings from the PDF that is somewhat uncertain. But effectively, irrespective of the uncertainties, you know that this star is in the inner halo. And it does fit with the picture that I was giving you of a star that's some kind of random orbit around the Milky Way, staying quite close into the close to the Milky Way center. And so we can do that for hundreds of stars, and by combining Gaia with the Pristine Survey and the spectroscopic campaign that I mentioned before, and also with LAMAST, Federico did this kind of analysis for hundreds of stars with metallicities below -2.5. And what I'm going to show here is a plot that's showing the orbital properties of stars. So I don't want to get into the details, it's a bit technical, but basically what you need to know in this plot, every single star will be a point, and stars that are on retrograde orbits will be on the left side of this plot. Prograde orbits, so turning around the Milky Way in the same direction as the sun, will be on the right side of this plot. And then the y-axis tells you how far away a star journeys from the galactic plane. So a star that stays close to the galactic plane on a prograde orbit like the sun will be down here. And a star that navigates far away from the plane will be towards the top. And if you indeed have that the older stars in the Milky Way were brought in this kind of very random fashion, you would expect that you have a symmetrical distribution of the stars in this plane, because you have as many prograde stars as retrograde stars, because they don't know where the disk is. And you probably have more stars down there than at the top, because you would need a lot of energy to send them far away from the Milky Way plane, but you would at least have something symmetrical. And it's actually not what we found by looking at the sample of a few hundred stars. What we found is that even at these very low metallicities, we have an overdensity of stars down there in that box that is quite significant. It's a 5 sigma overdensity, with stars with orbits that are not too dissimilar from the orbit of the sun. So it looks like the galactic disk is present at incredibly low metallicities, significantly lower metallicities than what was thought before. So then the big question is why? We offered multiple scenarios, and we're picking at every single one of them to try to figure out the one that seems the most the closest to reality. One possibility is that these very low metallicity stars actually formed in the disk. I personally think it's unlikely, because the disk of the Milky Way is made of gas that's actually quite enriched already, and it seems hard for me to believe that there would be pockets of very low metallicity gas left over. Another solution is that we're just at some level unlucky, and that the Milky Way has accreted a satellite that brought its stars on a set of orbits that are quite close to orbits of the disk. It's a bit contrived, but it's possible. The final solution is that we're actually here seeing the evidence of the very early assembly of the Milky Way disk. And in particular, then, instead of having maybe tens, hundreds of small blobs getting together in a random fashion, maybe the Milky Way and its plane was set by the fact that maybe two large blobs got together and basically imprinted the plane of the disk into as they merged together. And this is where these stars, old stars that were already created, got deposited, and this is where the disk then formed from the gas that was deposited with a similar angular momentum. Our look at Milky Way-like simulations, and also from other papers from colleagues, seems to show that this might actually be the favored scenario, and that initial scenario that I gave you of the Milky Way forming from multiple different blobs might be a little bit too simplistic. And actually a galaxy like the Milky Way might form mainly from large components that get together very early on. Unfortunately, even though we'd like to investigate that further, unfortunately most surveys of the halo look towards the halo. Most surveys of the metal poor stars that we think are in the halo look towards the halo. So we're kind of missing the disk portion where we might have a lot of these metal poor stars. But hopefully, again, we'll be able to expand the sample of these disky stars thanks to the agreement between Pristine and we in the coming years. The third scientific result that I want to touch upon, I'll be very brief here, is the work on the inner galaxy. This is work that's been led by Anke Aronson, and as I said, she'll be giving a seminar on this topic in June, if I'm not mistaken. So I'll be very brief here and just give you a teaser of what she's been able to do towards the inner Milky Way. And in particular here, one of the questions is whether the Milky Way has a classical bulge. Classical in the sense that it is made from material that was accreted over time through hierarchical formation, because the bulge of the Milky Way, and this is a beautiful image that's almost 20 years old from the 2-mass survey, shows this double lobed peanut shaped that is thought to be mainly because we're seeing a bar, so rotating component of the disk that is seen from the side. And what Anke's been doing is leading a particular part of PIGS that is focusing on the very center of the Milky Way. You see here the footprints of all the fields that she was able to observe towards the center of the galaxy. This is the very center of the galaxy. Of course, we can't get too close because the extinction of the dust becomes just impossible to work with. But she was able to combine this with a very systematic spectroscopic survey of the inner galaxy to get a good understanding of the kinematics of those stars, and also confirm and get metallicities from the spectra that will be more accurate than those that we get from the Pristine Survey on its own. Very briefly, I want to show that in the top right here, what you see is the histogram of stars observed from multiple spectroscopic surveys over time, that some of them that were not trying to select the metal poor bulge, inner galaxy. That's what you have here with apogee, for instance. And so, of course, it peaks at very high metallicities because that's where the bulge, the inner galaxy, is where the most metal-rich stars are. But then there's been efforts over time to try to selectively go for stars of lower and lower metallicities towards the bulge, because we think that this is where you can find the oldest stars in the Milky Way, as I was mentioning earlier. And you can see that with Pristine, the green histogram here, with the most efficient at actually probing these regions. And there's almost 2,000 stars with a metallicity below -2, thanks to the PIG survey. And so Anke is able to do a lot of exciting things here, looking at the dynamics of stars and their orbits, and their chemistry. But I'll leave it to her to present these results in a few weeks. The final science result that I want to spend a few minutes on is what we've been able to do with stellar streams in the Milky Way halo. Because we have this wide coverage of the Milky Way halo, the survey extends over more than 6,000 square degrees, we intersect a lot of structures that are present in the Milky Way halo and correspond to the leftovers, the fossils of past satellites, or dwarf galaxies or globular clusters that got shredded by tides in the Milky Way halo and gave their stars to the Milky Way halo. And this work would not have been possible without Gaia, and in particular, a piece of work we've been doing in Strasbourg, led by Rodrigo Ibata. And it's basically the development of an algorithm called StreamFinder, whose job is, to summarize very quickly, to test all possible orbits for all stars in Gaia and see which orbits look like they populated with many stars. And then by doing so and then figuring out the significance of these associations of stars, we've been able to find dozens of stellar streams in the Milky Way halo. You have a map here on the right of 2 distance slices from 3 to 12 kiloparsecs in the Milky Way halo in the top here, and from 12 to 30 kiloparsecs in the Milky Way halo at the bottom. And it looks like an incredibly busy plot, and that's the message that I want to convey, is that there's been a lot of stellar streams found. Some of them were known, like this GD1 fellow here, were known before Gaia, but most of those shown here were not known before Gaia. Most of them are likely coming from globular clusters that are either still that still exist, and now we have evidence that not only is there a cluster, but there's a stream of stars around them. There's Star 5 that's been known for quite a while, but there's quite a few other streams that we and other groups have been able to show are associated with known globular clusters. But there's also many thin streams that are actually coming from globular clusters that are now defunct, and has basically been completely shredded by tides in the halo of the Milky Way. And so these are really interesting for a lot of reasons, because we can try to figure out what was given to the Milky Way through time, but also because these very thin streams can be used, they're very sensitive to the nearby passage of the dark matter subhalo, so we can use them as seismographs and dark matter probes as well. But what I did about a year ago is actually combine these two projects, StreamFinder on one side that we had just run on the Gaia EDR3 a bit more than a year ago, and Pristine that's been accumulating these photometric metallicities over a large part of the sky to try to get a photometric metallicity for every single one of those streams, and also confirm that they existed because they had very consistent metallicity values throughout the different stars in a given stream. And the results were, I wasn't expecting that it would work so well. We have 20 streams that are in common between StreamFinder and Pristine. You see all those streams at the top here with the Pristine footprint shown in gray. And all the stars here correspond to stars that are significantly part of streams according to StreamFinder, and they're here color-coded by the metallicity that we get from Pristine. Here they color-coded just individually to see the different crisscrossing streams, because sometimes it's difficult to isolate them and separate them because they just overlap on top of each other if we just project them on the sky. And we're able that way to get a very homogeneous sample of stellar streams with photometric metallicities that we can compare to each other compared to the current satellites of the Milky Way, for instance. And you can already see, if you have a good eye, that there's also some streams like this one here called C19 that has stars of an incredibly low metallicity according to Pristine, significantly lower metallicity than anything else that we knew before this in the halo of the Milky Way or of any other galaxy. And so before I jump to that, let me just give you a broad overview of the metallicities we get from all these different structures. One thing that was quite surprising is that a lot of these, the metallicity of a lot of these new streams is actually quite low. You have here in blue the metallicity distribution of all the streams that are both in Streamfinder and Pristine. And if you compare it to the metallicity, for instance, of the Milky Way globular clusters, we're probing a regime that's significantly lower metallicity on average and extends to significantly lower metallicity overall. And some of these structures are actually lower metallicity than even some of the faintest dwarf galaxies that tend to be quite low metallicity. So it's quite exciting because we're probing something new. We're probably probing the leftovers of now extinct satellites that had somewhat different properties before, that were accreted onto the Milky Way earlier than what we observe now and got shredded by tides and gave their stars as stellar streams to the Milky Way halo. And so I want to focus for the last couple of minutes on this stream here, C19, that we discovered through that exercise, which is the lowest metallicity stellar structure that is known. There are stars of lower metallicities that we know in the halo of the Milky Way, individual stars, but it's the only conglomeration of stars of such low metallicities. And we think that this is actually the leftover of a globular cluster that was significantly lower metallicity than any known globular cluster that we've observed so far around the Milky Way or in nearby galaxies. And so the first thing we did when we found this low metallicity stream in Pristine is go to larger telescopes and confirm the metallicities of those stars. And you see here the 8 easiest stars to follow up. We got observations from 2 different telescopes and then that one star that appears in the MOST as well. And we're able to show that the metallicity of these stars is always the same. And so the dispersion in metallicity is incredibly small. It's basically consistent with 0, and it's we have a very strong constraint on how low it is. And that's quite typical of what you expect for a globular cluster, whereas a dwarf galaxy, which has a dark matter halo that can retain its gas for longer, will typically form multiple generations of stars. But then if we compare it to the metallicities of globular clusters in the local volume, this is, I've hacked a plot from Beasley et al. From the SLEX survey where they showed the metallicity of clusters in different galaxies. On the x-axis, you have different galaxies in the local environment, either dwarf galaxies on the left or the Milky Way here, and 31 Andromeda here, and larger galaxies. And on the y-axis, you see the metallicity that's been measured from spectroscopy around either the Milky Way or nearby galaxies. And you see that it looked like there was this floor in the metallicity of clusters with maybe 1 or 2 exceptions. This floor had metallicity about -2.5. And this new stream that comes from a cluster actually goes straight through that floor and becomes actually a significant problem for models of the formation of stellar clusters through the age of the universe, because in these very early ages where this structure must have formed, usually already models had issues forming things that were as metal poor as the previous floor. So it will be interesting to see how this new constraint changes the models and changes and constrain stellar evolution in the very early ages. Now, this structure in itself, and here I'm showing you the column magnitude diagram that we've been able to reconstruct from looking at stars with similar orbits to that stream. You see the red giant branch of that structure, you see the turnoff down there with quite a few stars, and you see even a blue horizontal branch of that system here that is at the right distance. So it looks quite typical of an old metal poor stellar population. What's interesting is that it's really a window into the formation of probably the first structures in the universe, the first giga-year or so, and it's very complementary to what JWST, the James Webb Telescope, will be able to do by looking at galaxies forming very early on by looking far, far, far away. And so it'll be interesting to see how these 2 pictures fit together or don't, and probably complement each other, because we can get more details on for instance, the chemistry of the stars in that system compared to what JWST will be able to do on maybe more systems by looking far away through lens clusters, for instance. And hopefully we'll find more with Gaia DR3 in a couple of months, and then with future follow-up WEAVE that we're involved in, but also Foremost and DESI and so on and so forth. And so with this, I'd like to summarize with just one final slide. I know that I've shown you a lot of results. I hope I wasn't too quick on them, but to summarize overall, the Pristine Survey that we've been developing over the last 7 years has been incredibly useful and incredibly efficient at isolating the lowest metallicity stars, so stars with less than 100th of the metallicity of the sun, and even lower than this. When we talk usually of stars at a field average less than -3 or so, they were probably formed in the first 2 gigayears of the age of the universe after the Big Bang. And so we're really probing the assembly of the first structures in the universe. With the survey, I've shown you that we're able to find the oldest stars and hopefully probe the star formation of the very first stars as we build a larger and larger sample of these lowest metallicity stars. We're able to lift the veil on the assembly of the Milky Way in its infancy by looking at combining our data with Gaia, for instance, looking at the kinematics of these stars, their orbital properties. We're able to uncover the origin of the many stellar streams that are found in the Milky Way halo, confirm that they're real, and start to look at what their chemistry is, at least first from their metallicity. And we'll, in the coming years, thanks to an agreement with the Spectroscopic Survey, we're pretty convinced that we'll be able to boost the numbers of known extremely metal poor stars from a few hundreds right now to probably 10,000, which will open up an era of large statistical samples that will hopefully help us refine a lot of the things that I've talked about today. Thank you very much.
Thank you, Nicolas, for the very nice talk, very interesting results, and for showing this in an easy way to follow your presentation. Now it's time for some questions and maybe some discussions. So let's follow the order of people raising hands. So first, Professor Jorge Melendez. Jorge, you can just open your microphone.
Hello?
Yes.
Hello.
Yes. Yeah, thank you for such a wonderful talk. I wonder, from the work that you are doing, I wonder if you have an idea already if most of the galactic halo was formed in situ or actually from accretion.
So at the moment, this is not something that we've explored in great detail. I think there's been work also from other surveys like SDSS. Some colleagues in the SDSS have worked quite a bit on that. I think it depends a lot on which distance you look at. If you look at distances of more than 30 kiloparsecs, I personally would be ready to bet that most or all of it is accreted. Now, if you come closer, within 30 kiloparsecs, my suspicion, and there's been some really interesting work and simulations showing that, is that some of the stars were formed in situ and they were just thrown up into the inner halo because, for instance, of the passage of a large dwarf galaxy that was accreted. And so on. It's not something that we've looked at in great details, to be entirely honest, but that might be something we should look into. And as we build a sample, especially with the spectroscopic follow-up with Weave, to look at how things change, maybe not so much as a function of distance, but of orbital properties and how far the stars can go in the halo, which might be more representative of a global quantity rather than just distance.
Thank you.
I myself have some questions, but I will allow first Maria and Betty. Please, Maria.
Okay, thank you. Thank you, Nicolas, for this great talk. Many thanks. I have a very naive question, because this is not my field, but I found it really interesting. I would like to ask concerning, you mentioned that you are interested in how the first supernova exploded. And I am wondering, at such low metallicities, how many supernovae candidates would you expect to have in your statistics, let's say, in your sample?
Yeah, absolutely. So I think if I remember talks from colleagues in the Pristine collaboration a few weeks ago, usually if you take like a dwarf galaxy and you let explode 2 or 3 supernovae, then you quickly reach a metallicity of about a field rate of about -2.5. So if we're talking about stars of metallicity -4, -5, like some of the lowest metallicity that we know nowadays, you're probably talking about a very small number of individual supernovae, maybe only a single one. And so that's one of the things that people are looking into, is once you look at the chemistry, do you have a chemical pattern, like a ratio of abundances that's similar to what you find in stars nowadays? Or, and that seems to be the case for a few stars found so far, you start finding weird patterns, like the ratio of different elements is different. And that could be the sign that these stars were formed from gas that was polluted by just one single first star supernova. And then you can start comparing that with different models of, rotating very massive stars, or many fancy models. And I think that's one of the holy grails of this search for the lowest metallicity stars, is to try to understand how many supernovae do you need, what were their properties very early on. And I think we're not quite there yet, right? We only have a handful that look really interesting in this regard. Hopefully with what we're doing in the coming years, we'll have a few tens of that, and then we can start comparing it with models in the statistical sense.
Yeah, that's really interesting, because maybe you will find something that you are not expecting. Like maybe the process is really slower back then than it is now. I mean, in terms of metallicity. And then I was wondering if you have a way to tell. You mentioned this star with a very low metallicity that was really poor in carbon. I was wondering, do you have any? I don't know. Do you know what type of star is this, or have you have any guess of the mass or something?
Yeah, it's a fairly typical. So this one I can't quite remember. I think it's a Turn-off star or something like this, and we by comparing with models, we can get the mass. If the models like the isochrones are accurate, we can get the mass, and it's a low mass star. I mean, it has to be lower than 0.8 solar masses, otherwise it would have already exploded into a supernova or evolved into a white dwarf. So there's nothing that looked outrageous, and that's one of the, I guess, one of the positives here is that, except if there's a lot of things that we don't know. These stars, if you just look at broadband colors, look quite similar to other stars, which makes it hard to isolate them. But at the same time, it means that we don't have to do something crazy to find them. They're there. We just either need a big enough bucket, like a big enough spectroscopic survey to find a few of those, or we need to be clever and find new ways to isolate them more efficiently, like with Pristine or other similar surveys.
Okay, I see. Okay, thank you very much.
Thank you.
Now, Elizabeth.
Oh, very interesting talk. Thanks. My question was in the same line as Maria Victoria's, the last question of Maria Victoria, about this very low metallicity stream of stars. If there is any clue on their origin, in the sense that, is it possible that these, you said that they belong to globular clusters in the halo, but is it possible that this peculiar, very low metallicity system was captured somehow during the galaxy formation, or in some kind of accreting process, as you discussed as well with George, or there are any other clues on this?
So we think it was accreted. We don't really see how it, because it goes, the orbit of that system goes out to 30 kiloparsecs in the halo, and the pericenter is 10 kiloparsecs. So it clearly is a halo orbit. And so in all likelihood, it was actually accreted. But what's striking is that the width of the stream it's quite thick, and thicker than what we would expect if it's coming from a globular cluster. And the velocity dispersion, which is a measure of the dynamical mass, effectively at some level, is quite high. And so, whereas if it were just a normal cluster, we would expect it to have a low velocity dispersion and be thin on the sky. So either it's because it's been going around the Milky Way for so long that it got beaten up somehow, either by the passage of nearby satellites or dark matter sub halos, or because it hit the disk every so often, that it bit by bit it just heats up and becomes thicker and thicker. Or it's because we're observing maybe something that's at the limit between a cluster and a dwarf galaxy. What if you have a dwarf galaxy, so gas and a dark matter halo that form stars, and then that stellar burst forms one cluster and then exhausts all the gas? Right. Then you would have something that has the dynamical and the signal of a dwarf galaxy, but has the chemistry of a cluster. And so we've really been struggling with this because we have a tension somewhere between the chemistry of the stars we observe and the dynamics of those stars, and we're trying to reconcile all of this together. It's really a fascinating puzzle.
Yeah, that's interesting. Yeah, it's an interesting point to to pursue. And actually, it might be, as you said, very interesting. Anyways, thanks a lot.
Thank you.
Well, I have two naive questions. One, when you showed some excess of prograde motions of the metal poor stars in the disk, excess. Yes. So when you analyze this data, do you see any excess also for the stars that go far from the disk in the upper part of this plot? No. The statistics shows it's more or less.
We haven't looked at it in great detail. There's some interesting signatures if you look at, indeed, not at the stars that look close to this, but stars that go far out in the halos. There's some interesting signatures. It's difficult at the moment to understand whether they're coming from just the way we observe those stars. So we just by observing stars in a particular part of the sky, you might have some selection that is imparted onto your orbits. But also it's made difficult, the analysis of those stars is made a little tricky because it depends a lot on what potential you assume to calculate the orbits. So if you assume a Milky Way potential that's very light, and there's been a drive in the mid-2010s for people to go for a light Milky Way of just less than 10 to the 12 solar masses, then your stars, actually a lot of the stars end up escaping the Milky Way. And so that I find that very odd that we would be observing a lot of stars around us that are on orbits that send them away from the Milky Way. So you have to be very careful on the potential that you use to do your integrations, especially if you're trying to look at where the stars are going. Are they going really, really far out or not? But it's something that I've been meaning to get back to and look at better in better detail about the orbits of those outer halo stars. Because we weren't finding necessarily that there was an asymmetry, but we were finding some structures, like there could be a bunch of stars in similar orbits. But honestly, we stumbled on this, and basically it was so unexpected that we focused on that result, and we never went back. But I should go back and look at also the stars that are far up there and see whether we can find something interesting over there.
Right, thank you. And another quick question is that I think you showed before some comparison. You showed that okay, the calibration is never perfect for the way you estimate the metallicity. You calculate the metallicity with the data from Pristine, and you compare with the spectroscopic data, and there is some sort of saturation. You showed some plots with some level of metallicity, and you give a zoom between -2 and -4, something like this.
Oh yeah, I see. So this one?
Yes. Yeah. So, okay, it's not perfect. You said maybe to look again into the models. My naive question is that this maybe some imprecision comes from using this color G-I as a proxy for temperature, or does this maybe this uncertainty, this effect of saturation coming from the neighbor lines, from the center of the filter? Or?
So we tried a few things. We tried using G-I as a proxy for temperature. We tried using G-R, because when we started, Gaia didn't exist yet. Well, Gaia existed, but we didn't have the data yet. And so we didn't have this beautifully calibrated Gaia data. So we were relying on BSDSS that was publicly accessible. We found that using G-I was significantly better, for instance, than using G-R, which is why we focused on this. But it is also true that all these relations that relate temperature to color are only averages, and sometimes you have some weird things happening. We've been using also SDSS, which is better calibrated. Gaia, which is better calibrated than SDSS. Unfortunately, the Gaia filters are very large, and so then you end up having the kind of issues you were talking about. Like, for instance, if you have dust, then your color does not directly. If the dust content changes, the color does not directly transfer into a change in temperature. What we're looking forward to is the third data release of Gaia on June 13th, because it will, for a lot of the stars, for probably a couple 100 million stars, if not more, there will be some temperature estimates. There will be some log G estimates, and there will be some metallicity estimates that are coming from the Prism Photometry. So this BP and RP that were basically the integrated filter is now It's Prism Photometry, and so they'll give us the Prism spectra, so the very low resolution spectra, and they will have derived metallicities from those. So we're waiting to see how accurate those metallicities and those temperatures are, but it will be useful to have more information to try to refine these calibrations. But just to finish, another thing that has really caused trouble for us, but Gaia has helped, is the fact that if your star is varying, if you go back to that color plot that I was showing before, the broadband from SDSS, it's a scanning of the sky where they scan with the 5 filters at the same time. So if your star is varying, the broadbands G and I were observed at the same time. But then we observed calcium H&K years later. And so if your star has any type of variation, whether it's short-term or long-term, your star can be anywhere in that plot, basically along a vertical axis. And thanks to Gaia, we're able to clean out a lot of that, because Gaia tells us the variation from epoch to epoch, and they've observed tens of epochs. And so we know that the star seems to vary more than it should. And so there's constantly improvements that can be added by using new data, but we need to make sure that the data is covering as much of the sky as possible, because if you go and add another survey that has another footprint, then you just make things smaller and smaller, right? So Gaia is incredibly useful for us because it's all sky. Every star we have is in Gaia. And so we've really been relying on Gaia more and more, and the next data release in a couple of months should be extraordinary for what we're doing.
Thank you. Now we go to our last question, Georgie.
So Nicolas, you say that at the lowest metallicities, you can have just one supernova explosion, right? Just to get the star.
Yeah.
But
yeah.
So what do you expect about the metallicity distribution function at the lowest metallicity? Do you think that it will just flatten out at some point, like let's say below -5 or so? Or do you think that it will become progressively, exponentially smaller and smaller?
So it seems to flatten out from the data that's accessible right now. It's not pristine work, it's beautiful work done by a lot of colleagues over the last 10, 20 years. It seems to flatten out. Because effectively we find as many stars with metallicity between -4 and -5, or -5 and -6. Whereas before, if you go to -2 and -3, you have a ratio of like 8 or 10. So it does seem to flatten out. Personally, I'd like to have way more data, because every single star is weird in that regime. And I'd like to really be able to build a metallicity distribution function from -2, -3, where we are right now, all the way down to -5, -6. And again, as I mentioned before, I think thanks to Pristine plus Weave, but to also other surveys that are ongoing right now, hopefully we'll be able to really boost the statistics in this regime, to be able to really compare to models and what's expected. If every single star in this regime can only be polluted by one single supernova, then what does that tell us for the metallicity distribution function, and can we start discriminating between models?
So from that point of view, so what is the cutoff metallicity from what we can say, okay, these stars were originated just from one single supernova, -4 or -3? Do you have an idea?
No, not exactly. I think it depends on the conditions, right? If your star forms at the edge of a cloud that was polluted by maybe 2 supernovae, maybe you will show up as being -4. But what I can say is that there are a few stars now of incredibly low metallicity, like -7 or -6, if you overreach -7 or -6, that look like they have weird patterns in their chemistry and the ratios of the different elements. And so then I think we're starting to probe a different regime, something different that might also not just be like being polluted by one single supernova, but being polluted by one single supernova that might have been the first star. But first of all, I'm really not an expert of that particular field, so I don't want to say something stupid, but also I think we really need to build statistics over there. And that's personally something that I hope to bring to this field, is being able to develop these large samples that then can be studied by experts with detailed chemistry to try to understand what that tells us about the very first stars.
Sure, thank you.
Okay, I would like to thank you again, Nicolas, for giving this seminar, for giving us your time, for sharing your research, your knowledge. Yeah, thank you a lot.
Thank you for the invitation.
And now we will finish the YouTube broadcast.